The next talk is by Eugene Kotomin, who's worked for a long time with Patrick, and he's talking about the first principle of modelling and non-geometric perovskite. Thanks,
This
Eugene.
is the slide changer and what the pointers at the top.
Okay, so I would like to say that I'm very happy to be here to remember Patrick and tell a little bit about our joint research. So I'm Eugene Kotomin from Institute of Solid State Physics, University of Latvia. And also, essentially, I'm spending a lot of time in Max Planck Institute for Solid State Research in Stuttgart, in Germany. Okay, so I would like to say that it's a little bit, cut the margin. That I have known Patrick not so long as many of you, but still from 1990, when Alex Schluger and me organized the first international conference on quantum chemistry of solids in Riga, University of Latvia. And it was the end of Soviet period, and it was not so easy to organize international conference. Everything was have to be improved, and to get speakers again it was not so easy. But Patrick was very open, and he immediately agreed to come, and he was very supportive of us. Essentially, when we organized two research groups in the University of Latvia, Alex in chemistry, me in physics. And since then, we collaborated with Patrick on several topics, including metal oxide interfaces, self-trapping of carriers in ionic solids, and defects and surfaces of perovskites. So these were three essentially main topics we collaborated with Patrick. And essentially, conference is very successful. Fowler was there, Pisani, and the leading people in quantum chemistry and defect chemistry and physics. But at the same time, conference turned very dramatic way because Patrick's wife died during the conference very suddenly. It was a great shock, essentially, for him and for all of us. And it was very dramatic event. So I was, next year I was fellow of Center of Chemical Physics, what Patrick established in the University of Western Ontario. And during collaboration and my visit and several other visits to University of Western Ontario, essentially very much shaped my research personality, let's say. Because Patrick was so great teacher and so great scientist, so I very much appreciate our joint research. So in that period, next 10 years, we published 25 joint papers. And as mentioned, this is, for instance, example, this is metal oxide interfaces. So it's author our joint paper is Marshall Stoneham. So one of papers I like very much. This is another paper on self-trapping of holes in alumina. Unfortunately, it was never experimentally proved, but theoretically we try to persuade people that it's possible. And now I will give just a few examples of what we did on the third topic, which is essentially defects and processes in in perovskites, ABO3 type perovskites. So we performed this particular number of calculations on defect formation and migration in potassium nitrate in particular, which is important for applications. And since then, I continue calculations for perovskite, but now much more complicated materials. So I will just give you examples of what we did recently, but all this was inspired by our work with Patrick. And essentially, it's a mixture of quantum chemical calculations and kinetics of processes. So essentially, what we are working in Max Planck Institute and also University of Latvia, it's understanding of basic properties of solid oxide fuel cells and also permeation membranes in order to improve materials and to reduce operational temperature of materials to so-called intermediate temperature solid oxide fuel cells, which is strongly technologically demanded. And for this we have to understand, these details essentially of oxygen reduction. When oxygen from this phase comes to the cathode material, which usually is perovskite, and oxygen just reduces into O2 minus, goes through electrolyte, comes to the anode, and at anode it starts a chemical reaction with hydrogen containing some gas, and essentially this chemical reaction energy is transformed into electricity, because electrons are just coming here and released from hydrogen molecule when it dissociates into protons on the anode. So essentially, chemical process is just coupled to the generation of electricity, and it's the idea of the fuel cells, which is very simple, but the question is just to find optimized materials. We could work, this just oxygen reduction could work essentially at not 1000 Kelvin like now, but say 600, which would be a revolution essentially in technology and reduce just these fuel cells price by order of magnitude. So it's a very exciting, challenging field, including electrochemistry, materials chemistry, software science, chemical kinetics, and also large-scale computer simulations. And we tried, piece by piece, to study these processes. So goals of theory essentially are to understand atomistically details of oxygen reduction, in particular what are oxygen formation energy, migration energy in the bulk and the surface of this cathode materials, optimize chemical composition, and challenge is to understand what are rate-determining reaction stages, and from this we could just optimize materials and reduce operational temperature. This is our dream. And this is just a very, very clear message and very clear summary from experimental studies of the efficiency of oxygen reduction on the surface of cathodes for three classes essentially of perovskites used for these applications. The first one is so-called lanthanum manganate doped with strontium, which is abbreviation is LSM, usually just very simple way. So next, more complicated when we have a solid solution, then on A side of perovskite, A side lattice, we have lanthanum and strontium. On B, it's cobalt and iron, so it's called LSF. And the most efficient material is nowadays is barium, strontium, cobalt, iron, which is called BSF. And essentially, if you look at this, just efficiency, so you can see that LSM has the lowest efficiency, essentially because concentration of oxygen vacancy is very low, and for high efficiency you need fast oxygen transport, and since you have not enough oxygen vacancies, so there is no fast transport. It's very simple. Next, materials in LSCF, and in this case you can see that concentration of, so it's more non-stoichiometric, it has high concentration of vacancies, and immediately you have increased efficiency by 2 orders of magnitude. But what's the most interesting is the next step. If you look for, if you replace lanthanum for barium in the same particular material, immediately you have increase of the efficiency another 2 orders of magnitude. In this case, I mean, concentration of vacancies are comparable, but the difference is that now you have much more mobile vacancies. So mobility, migration energy is half of this, essentially. It's half EV compared to 0.9, I mean, EV typical migration energy in perovskite. So in this case, for materials as BSF, you have both very highly mobile and very high concentration of vacancies. And essentially both are just important for fast oxygen transport. And we studied these materials last years, just to understand from so-called ab initio level what was the reason why these materials are so efficient. And in principle there are several, it's trivial probably remark, but it's there are several ways for development of new materials. One is combinatorial, and for instance there are groups which performed, I mean, essentially hundreds of routine calculations changing composition experimentally, and they're quite successful to make trends and to understand, I mean, what should be changed, I mean, to get more optimal materials, but still there are fundamental problems and limitations of experiment. First, you can't discriminate surfaces as a surface and the various surface, essentially, and in the bulk or near surface. And in the case of just oxygen reduction, you need to understand the reaction between surface vacancies exactly and absorbed oxygen. Experimentally, you can't distinguish, I mean, vacancies in the subsurface area and the various surface. And second, okay, theoretically you could easily, I mean, look for different role of different impurities and dopants, and also identify adsorbate at low coverages with experimentally with a challenge. So what we are doing in Max Planck is a kind of large-scale computer modeling of advanced materials for these applications. And these are just several references, review articles, what we just summarized what we did recently. So if somebody is interested, you could find more details. Also, what is missing here is just chapter of a book on energy materials published edited by Richard Ketlow, which was published just this year. Very detailed chapter about this computer modeling. But all this, what I would like to stress is just about reducible oxide chemistry and just Hobart and Tyro properties in these materials. So just technically we use just absolutely standard computer code. We use VASP which is commonly used in essentially density functional calculations in solid state physics. And we use crystal code with atomic basis set. And essentially we also studied, I mean, these calculations of perovskite with Patrick. So we used with Patrick when I came to him first interatomic codes, so Cascade and Gulp, and very successfully. And then we started just during my visit, just quantum chemical calculations of perovskites, what we continue now. And nowadays we could easily use in this calculation so-called hybrid functionals, which is important for calculations of defect properties because you need a very accurate band gap to put energy levels within gap. So a typical example is strontium titanate. If you calculate Hartree-Fock gap, so instead of 3.5 micromole gap, you have 6, and FT gives you 1.5, so twice overestimate, twice underestimate. And with hybrid, you have error about 10%. So it's more or less good quality. And the latest parameter and all this could be reproduced with 0.5% error. So we use a standard supercell model, which could be cubic or not cubic, extended with several hundred atoms. So it's nothing special. This is just sketch of the 40-atom supercell. So we just remove some oxygen atoms from here and obtain essentially effective structure that we calculate. And I would like to stress that this material, barium, strontium, cobalt, iron, BSF, at the moment is the most efficient material. And also one of reasons why it's so efficient is that because it's very strongly non-stoichiometric. It means that this delta would be something like 0.7. So it's not 3, but oxygen 2.2, 2.3. So it's a huge concentration of oxygen vacancy, intrinsic, present in these materials, which is necessary again for very fast oxygen transfer. So essentially, we studied, how properties of these materials, of say, in particular BSF, depends on the fraction of iron when we have different ratio of cobalt iron. So it's iron concentration changes. So it's pure cobaltite, and this pure iron, essentially. And this is just vacancy formation energy. And you can see that vacancy formation energy has very clear trend with composition in B sublattice. So this allows for cobaltite, the formation energy could be 1.2 electron volt, and it increases practically twice when it's iron rich. So it means that cobalt rich material essentially has much formation energy. What essentially you would like to have. And also when you have mixture of say cobalt and iron, oxygen vacancy has different local surroundings. Essentially it could be vacancy surrounded by cobalt iron, cobalt neighbors, and all this. So we calculated also different configuration, but you can see that okay, it's not so important essentially. At any rate, trend is very clear. And essentially, it's in agreement with some experimental data which indicates defect concentrations in BSF is much higher than in barium, strontium, ferrite, when cobalt concentration is low. So it's supported by experiment. But also what I would like to stress that this so low formation energies explain why it's so much non-stoichiometric at high temperatures, operational temperatures, like 1000 Kelvin. For instance, in strontium titanate, standard perovskites, formation energy is about 6 electron volt for vacancy. And for lanthanum manganate of strontium, it's about 3. And here it's again much smaller. And why cobaltite is so efficient could be understood from the analysis of density of state. Essentially, for iron, we have high spin configuration, and for cobalt it's intermediate spin. And if you look at this diagram, it's alpha and beta spins. So essentially, it means that for beta electrons, this peak of cobalt is overlapping with Fermi level. And for iron, it lies much less in energy. So when you create oxygen vacancy and electrons go to nearest cation, big type cation, so cobalt easily accept electrons, so Fermi level changes a little bit, and most of electrons easily go to cobalt, but not to iron, because to get to iron it needs much higher energy. So it just very simple chemical understanding why cobaltides are more efficient. And next question is again about essentially not only formation but migration energies. So we also calculated migration energy for different configurations, and I mentioned that in initial configuration and final oxygen vacancy has different neighbors. It could be cobalt iron, cobalt cobalt, and so on. So there are several configurations. We calculated all this, and also, but you should be careful, because this in this structure is quite loose, and essentially this diffusion path is not linear, but it's curved. And if you just don't take it into account, your migration energy could be essentially in error by 50%. And we discovered also this particle again when we started calculations of perovskite, so potassium niobate in 92, something like this. So okay, at any rate, if you calculate all these migration energies, you come to the conclusion that migration energies average could be something like half EV. And for comparison, all perovskite, essentially all other perovskite plus strontium titanate, lanthanum manganate, all these materials give you almost twice higher migration energy. So barium, essentially BSF, is exceptional material for very low migration energies, as is why very fast oxygen vacancy transport. And again, we studied how migration energies depend on the concentration of iron in composition. And again, we found the same trend. So the formation energy is lowest for cobalt-rich composition, and it increases again almost twice for iron-rich. It's similar to formation energies. So essentially, once again, so this material has extremely low migration energy. And we tried also to understand what was the main factor behind this, low migration energies. And essentially, it's not so easy. So we spent, a couple of years and published a number of papers, and this review article just explained in more detail. But first of all, the simple geometry arguments of BSF, due to large barium, has quite larger lattice parameters than other perovskite. So naively, there is more space, for say oxygen atom to jump to vacancy, and this could be a reason why it's smaller. But first of all, if you look for standard, analysis, people try to use using this ionic radii, so-called Shannon analysis. It's not really correct, because essentially there is considerable covalence in these materials, and it's not oxygen 2-, essentially these materials you find effective charge and minus 1.5 or something like this. And also for B cations especially, this also considerable covalency and bonding between B type cation and oxygen. So first you should very carefully redefine what are ionic radii in these materials, so we did. But also, if what we found, there are three essentially key factors determining migration barrier. So first is essentially, it's shown here. So essentially, in the settle point or in transition state, oxygen goes through triangle of two A-type cations and B-type cation. And the first factor is just deformation of this cage. And when it's more space, so essentially it's easier to migrate and energy will be smaller. This is okay, the first essentially important factor. Second, very important what we found is again there is charge transfer between magnetic oxygen and B-type cation. And essentially in this material there is considerable, in BSF, considerable charge transfer. So oxygen becomes smaller and it easier goes through. And if you take, for instance, LSF, in this case there is almost no charge transfer and energy becomes essentially larger than in BSF. Second, essentially the whole structure is also deformed during the migration, and there is a tilting of octahedra in this structure. So it's not even local, but it's a distortion which is just cover some local volume of several tens of angstroms. And as I mentioned, there is also important covalence and change of covalency between B-type cation, cobalt for instance, and oxygen going as a saddle point. So this is just sketch of the electronic density distribution when vacancy jumps into this position, and this is just transition state and the covalence between these two, and charge transfer just controls essentially the migration energy. And this is just sketch of the structure, just illustrating what I saying. So when vacancy jumps, oxygen atom jumps into vacancy here, you can see that the whole structure in about 8-10 angstrom around the vacancy is distorted, and you can see this zigzag, just distortion of the structure around saddle point takes place. And essentially we tried to rationalize this migration energy in perovskites. We calculated number of related materials, something like 20-25 different materials, as a function essentially of deformation of this triangle during the we call it geometrical factor, okay? When oxygen atom goes through a triangle A prime B cation. And also vacancy formation energy. So it's clear trend that migration barrier would be presented as a function of both. And essentially it's not geometry distortion of the structure distortion, but also electronic structure is important, because we have a clear trend that vacancy formation energy is related to migration energy. And essentially BSF, you can see that just is here, so it's the lowest migration energy. Okay, so step by step we calculate energetics of all essentially elementary processes in oxygen reduction in order to calculate reaction rate and to find out the rate determining steps. And this is illustration what we did for lanthanum manganate and now I performed for BSF. So essentially this illustration that oxygen is adsorbed in the manganese terminated surface like tilted molecule. Next it could dissociate, which take energy, quite low energy, about 0.6, 0.8 electron volt, which is energetically very favorable. So as a result of dissociation of oxygen molecule at the surface, we have two minus ions sitting above manganese. And next, again, question is how this oxygen adsorbed oxygen atoms meet surface oxygen vacancies, because this is just the first process which triggers oxygen penetration into first plate and next migration through cathode material to the anode. So we need just reaction between surface vacancy and absorbed oxygen. And again, experimentally you can't discriminate who is more mobile because it's diffusion controlled essentially reaction. So from again computer modeling, we found that essentially absorbed oxygen ions are quite immobile. So migration energy is about 2 electron volt. Whereas surface vacancy are even much more mobile than in the bulk, and migration energy is about 0.7 electron volt. So essentially our scenario is that surface vacancy are very mobile. They essentially approach absorbed oxygen atoms, and then that triggers penetration of oxygen from the surface into the first plane and to the first bulk. And again, and this so already determining steps are shown here, essentially by pink. So it either molecular dissociation or it's diffusion as a vacancy of the surface. And again, what's important is that at high temperatures you should take into account that entropy effect essentially are crucial, and you should take into account vibration degrees of freedom of oxygen molecules. So essentially this entropy contribution could be about at 1000 operation temperature 1000 Kelvin, about 2 electron volt. And it means that this diagram of 0 Kelvin should be modified at least at 0 approximation by this one, which is blue now. And instead of energy gain due to oxygen molecular absorption, essentially you need some energy to absorb oxygen, which changes amine reaction rate very much, and you should be careful about this. And, as a result, okay, we made some prediction for reaction rate for a number of perovskite cathode materials, and also we try to understand difference between BSF, barium strontium, and LSCF, platinum, and this big difference. And I mentioned that difference is also in particular because we have different charge transfer for oxygen in the migration phase. And this is why use of paired potentials in this delicate, I would say, modeling turns out to be quite limited. So probably I just start to finish. So probably I just summarize by saying that essentially what we are doing is just was inspired by our work with Patrick in the 90s when we studied just processes in perovskite, and now we able to study much more complicated materials. And also, this is not the end of the story, because as I mentioned, these materials like BSF are the most efficient for oxygen reduction processes, but it was discovered recently that they're unstable with respect to the transformation from cubic phase to the hexagonal phase. When temperature is decreased from operational a little bit lower, and when it's hexagonal phase, its properties are lost essentially. So materials are unstable with respect to transformation, and essentially what we are working now is just again in spirit of Patrick interest in decomposition processes. It's another illustration of these problems. We study structural instability of these materials, and this is just another story published in a recent paper. So we understood, essentially there is like in Chinese symbol in yang. So nothing is perfect, and when you have some very positive, it has something at the same time some negative properties. Okay, so the fact that structure contains so high concentration of vacancy, so mobile vacancy, turns into instability of this material. Right? is no essentially solution, and could be only compromise probably between these two properties. So I would like to finish by saying that essentially this picture I didn't tell in the beginning was taken in Riga during the conference what we organized in 1990 during excursion in the old city. So Patrick looks very happy at that time. So Patrick was not only a brilliant scientist and teacher, but also a good friend, great personality, and we always remember him with great pleasure, respect, admiration. Thank you.
Question?
Eugene, you said the oxygen vacancies are more mobile on the surface. Well, what's the difference in the activation energy between surface and bulk?
In these materials it was lanthanum manganate, so in the bulk it was 0.85 MV, something like that.
And what about 0.7 on the surface?
It was roughly 0.9, 0.7.
Yes, it's not crucial.
Because it changes order of magnitude
Yeah.
of concentration immediately.
Yeah, just follow up on that. I think the one of the factors there is also that the deformation energy of vacancy on the surface and in the bulk is slightly different. And then there is a gradient of chemical potential for the migration of the vacancy into the surface, right? And that possibly balances the equilibrium concentrations at given conditions. And talking about the conditions, this is important work, and it reflects, I guess, all the tendencies, or most of the tendencies, which are important in electrochemistry, in this particular essential electrocatalysis process. But we know that the process itself is very much controlled by the voltage as well, right? So the question is, well, first of all, how we deal with the voltage. So there are ways of dealing with that, but how good they are, how adequate they are in terms of the first principle calculations, it's a big question, it's an open question. And the second one is that would the question about the voltage or external electrostatic potential change the tendency or add something new to the tendency, you think?
Very good question. But essentially, nobody succeeded, I mean, to take seriously voltage into electrochemistry, to my mind. Norskov and other people just to do it essentially semi-empirically, but it's still open question. So it's unsolved problem.
Can I ask you one quick question, Eugene? It's all very nice, but have these cathode materials also need to be mixed with electronic conductors?
The mixed electronic, they should be mixed electronic conductors, because you need both electronic conductor and this is one of the issue.
Yeah.
Main issues essentially to have mixed conductor. Absolutely.
Okay.
Okay. Thank you.